Hello and welcome to this video about matrix proofs. This is part of a collection of proofs in linear algebra. Since this is the first chapter in the book, then these proofs are labelled 1 point something. The first of these proofs is a proof about matrix addition. It contains these 5 parts. We can represent a matrix using this entry notation. The entry in the brackets will always be the ijth entry for any matrix being represented at the time, even if it contains lots of other variables. And this is the matrix that it represents. The entries in matrix A are small a's with indices, so that the first indice represents the row and the second represents the column. So now to prove part A, that matrix addition is commutative. We'll start with the left-hand side and get it into this sort of matrix entry notation, so that we can look at what entry this matrix contains at any location. So we can add the entries together like this, because this is how matrix addition is defined. We can perform this swap because it's a swap between numbers, usually real numbers and sometimes complex numbers, which are commutative. So now we can separate the entries like this. And finally we can get it back into the proper variable names of these matrices A and B to get the right hand side of this equation. And this proves part A of this theorem. So now to prove this associativity property of matrices. We'll start with the left-hand side and get it into matrix entry notation to watch what happens to all of the entries of a matrix as though it was one expression. We can gather together whatever's in the round brackets first. Then we'll gather the next term and we'll put brackets around the terms that we added first. We can swap these brackets because these entries are associative. They are usually real or complex numbers or any sort of field. We can separate out the term that's not inside the round brackets first. Then we can separate the next 2 terms, keeping them in round brackets, because they were more recently separated out. And so we can substitute the proper variable names back in for these entry expressions, which gives us the right-hand side of this equation, thus completing the proof of part B. Now to prove part C, which is a distributive property. The variable A is of the same type as the entries of this matrix and is usually a real number. We'll firstly write these matrices out in ijth entry notation. And we can bring these entries together into the same square brackets as though we're describing the entries in the matrix A plus B. Then we can bring the variable inside the square brackets, describing the matrix small a times a plus b in brackets, while keeping the entries together inside the round brackets, using the definition of matrix multiplication by a scalar. We can then expand the round brackets that control the order of operations. Then we can separate out the entries like this. Then we can take the variables out of the entries as though we're multiplying a scalar by a matrix on the outside. We can then substitute the proper matrix variables back in, thereby getting the right-hand side of this equation. And so now we've completed part C of this proof. Now to do part D of this proof. This is a different distributivity property. So we'll start with the left-hand side and use ijth entry notation. Then we'll bring this scalar inside the square brackets while keeping it inside the round brackets, treating it like a single scalar. Then we'll expand the round brackets. We can separate out these terms inside the square brackets, treating them like separate matrices. We can take the scalars outside these square brackets. Now these terms are scalars multiplied by a matrix, using rules for scalar multiplication by a matrix. Finally, we can write out the matrices using their proper variable names. And so we've gotten the right-hand side. So we've completed the proof of part D. And finally we've got to prove part E, which is a property of multiplying 2 scalars by a matrix in different orders. So we'll start with the left-hand side and use ijth entry notation. We'll use scalar multiplication rules to bring this scalar inside the square brackets. And we'll bring this scalar in next, but keep round brackets around this scalar and entry to show that these 2 numbers were multiplied together first. We can easily swap the brackets because these are numbers or elements of a field that have this property. Then we can treat the number AB as a single number because it's inside round brackets, and then we can bring it outside the square brackets. And finally, we can write out the matrix proper variable name, giving us the right-hand side, and so proving part E of this theorem correct. So that's it, we've proven this theorem. We can draw the small black square to show this. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write any helpful thoughts in the comments and to share this video. And thanks a lot for watching.